Hi friends, now I would like to represent about the designing of the 4-bit arithmetic adder. So this is the 4-bit arithmetic circuit. We are already discussing about the how to design the for arithmetic operation one a adder, two a adder and a subtractor which is able to perform both addition and subtraction. Adder performs the only addition and increment circuit, incrementer, and also a decrement circuit to perform the decrement operation, decrementer. So increment means suppose the content is a plus 1, the decrement is suppose the content a minus 1. It is perform both addition and subtraction, and the adder can perform only the addition, right? And we are also know that there are 7 arithmetic operations, right? I revision all these things. The first operation is the addition. We are going to write that R1 replaced with R2 plus R3. That is the content of R3 added to R2 and result is stored in the R1. This is known as the addition. And the second one, R1 replaced with R2 minus R3. We may call this operation as subtraction with borrow, because in subtraction digital circuits we are going to be performed like that. The third one, R1 replaced with R2 plus R3 bar plus 1. We know that this is the 2's complement subtraction. This is actual subtraction. We can calculate the 2's complement to the subtrahend and add it to the minend, right? The fourth operation is the increment. R1 replaced with R1 plus 1. That means we add 1 to the least significant bit of the content of the R1 and and the result stored in the R1. So the total value of R1 is increased by 1. The fifth one, R1 replaced by R1 minus 1. This is the decrement operation. And the sixth one is R1 replaced by R1 bar. We know that this is one's complement operation. And the seventh one is R1 replaced by R1 bar plus 1. We know that this is the 2's complement operation. Just I revision all these operations, 7 arithmetic operations, right? We already discussed in one video, but for our remembering purpose, these are 7 arithmetic operations, and we already designed in our previous videos these circuits to perform these arithmetic operations: adder, subtractor, increment and decrement. Now we are going to be design one arithmetic circuit, 4-bit arithmetic circuit, which is able to perform all the 7 arithmetic operations, not only this one, and also it is able to perform transfer data transfer operation also. To do this one, I am going to design a 4-bit arithmetic circuit. Now I design the 4-bit arithmetic circuit with the help of the full adders and multiplexers. I remind you the full adder, we are representing the full adder is like that. The full adder is a combinational circuit which is able to add the two, three bits of the binary. Suppose that is called one bit is A and another bit is B, another bit is C. See, I am here, the C represent the carry and it is able to generate the sum. Yes. So S is the combination of, that is I am going to write S equal to A, A plus B plus C in, that means carry in. So the full adder is a combinational circuit which is able to perform addition of the three binary bits. In the same way, the multiplexer, actually we know that the multiplexer is also a combinational circuit which is able to take the 2 to the power of n inputs and generate one output. That means the one of the input is turned as the one output based on the selection lines. Now here I am going to be consider 4 by 1 multiplexer. That means it has the four inputs. The four inputs are A, B, C and D. Two selection lines S0 and S1 to determine which of the input is turned as the output and one output that is known as the Y. The value of Y we determine as based on the output determine these selection lines S0 and S1. Suppose the S0 and S1 values are 0, 0. The first input A is turned as the output. A is turned as the output. Suppose the selection lines values 0, 1, S1 not value is 1, S1 value is 0. The second input, that means this 0 input, this is first input, second input and third input. So the first input B is turned as the output. Suppose the S1 and S0 values are 1, 0. The second input of the multiplexer, that is C, is turned as the output. Suppose the S1 and S0 values are 1, 1. Then the third input of the multiplexer D is turned as the output of the multiplexer. All these things we already discussed, but before we are designing of a 4-bit arithmetic circuit, we are using these full adders and multiplexers. Hence, I am remind to you now how I am going to be draw this circuit. So, to draw the entire circuit, it is a little bit problem. This because this is a very big circuit. Hence, I just refer only one stage of the arithmetic circuit for our understanding. Now let us consider this is the I draw. Please observe carefully. This is the full adder, right? FA, right? And this is the and this is the 4 by 1 multiplexer, right? 4 by 1 multiplexer. We know that the multiplexer has the four inputs that equal to 0 input, first input, second input and third input actually, and two selection lines I am going to be draw like that, the selection lines, right? These two selection lines S0 and S1, right? To perform the arithmetic operations we need the two operands, so that A operand A is directly connected to the multiplexer and operand B values are connected to the multiplexers. So this is the B. That means the 0 input of the multiplexer directly connected to the B, and complementing of the B input is connected to the first input of the multiplexer. The remaining two inputs of the multiplexers are connected to like that. Now I am going to be consider one NOT gate, and here input is 0, uh, right? This is connected to the 0 input is connected to the second input of the multiplexer, and the output of the NOT gate that is connected to that means all ones is connected to the third input of the multiplexer. Now the output of the multiplexer is connected to the second input of the full adder. We know that the full adder has the three inputs. One of the input is the one of the operand A, and the second input is the output of the multiplexer Y, and the third input of the full adder is the input carry Cin, and the output of the multiplexer is represented as D. And suppose there is any carry generated by the multiplexer, this is C out. Now, how this will be work, I will explain to you, right? Suppose now I am going to be consider the output D is performing the all arithmetic operations D equal to, right, A plus Y plus Cin. This is our final Boolean expression to get the all arithmetic operations by using the multiplexers and full adders. Now, how this circuit will work out, I will show to you, right? I will show to you. Now we are going to be consider, otherwise I am going to be explain in the same, please wait. Oh, sorry, this is not possible here, right? I am going to be show you here. Now based on the selection inputs, the multiplexer will generate the output, right? So once again I am going to be draw here, sorry, this is the full adder, the same circuit for our understanding. Full adder, the one of the input of the full adder is directly connected to the operand A, and let us consider there is a 4-bit multiplexer, 4 by 1 multiplexer. This is the 4 by 1 multiplexer. For 4 by 1 multiplexer, this is the 0 input, this is the first input, this is the second input, and this is the third input. The first input is connected to the operand B. The second input is connected to the complement of the second operand B bar. So the remaining two inputs are connected to the, right. We are going to be consider one of the NOT gate. The input of the NOT gate is 0, right. The second input of the multiplexer is connected to the logic 0. The output of the NOT gate is logic 1. That means the third input is connected to the of the multiple connected to the all ones. The output of the multiplexer represented as Y. This is connected to the second input of the full adder. Which of the inputs are considered as the output? We are going to be use two selection lines. I am going to be consider this is the S0 selection line, and this is the second selection line S1. S1. We know that the full adder is the three inputs. This is the C in. This is the final output of the arithmetic circuit D. And is there any output carry? This is C out. Now we are going to write the Boolean expression. D equal to, that means final output of the arithmetic circuit, D equal to A for the full adder, A is the one input, plus B, no, sorry, not, there is no B, the output of the multiplexer as the input to the full adder, that is Y, plus the full adder consisting of one more input, Cin. So this is the final Boolean expression. Now, how this circuit will work out, I will explain. Right, I derive a truth table. This is the selection line S1. This is the selection line S0. This is the carry in input, and this is the output Y, and this is the operation. What kind of the operation is performed? And we are also be consider this is as a D output. So S1 and S0 values are 0, and C in value is also be considered as the 0. So S1 S0 0 here, let us consider 0 0 and Cn is 0. So 0 0, the first input of the multiplexer is turned as the output of the multiplexer and input as the full adder. Now B is transferred already. Here we observe that A is also be transferred. The Cn value is 0. Now what happened here means A is, sorry, the y value is b, and the final is the a plus b at D. And suppose we are going to be consider S1 value 0, S0 value 0, there is C and there is an input carry. Now the y value is b, the final operation at the full adder is y value, because S1 and S0 values are 0 0, the first input of the multiplexer is turned to as a Y, that is the B is come to Y, and A is directly come to the full adder, and Cn equal to 1. Now the value is A plus B plus 1, that is add with carry, addition with carry. The first operation is simply addition, right? In this way, now I am going to consider S1 equal to 0, S0 equal to 1, and there is no input carry. The second input of the multiplex, sorry, the first input of the multiplexer, B bar, is turned as the output of the multiplexer. Now here, the value of Y equal to B bar, A is directly come to the full adder, A plus B bar. Here, 1 is missing. This is subtraction by borrow. Subtraction by borrow. The next one is I am going to be consider 0 1, and there is an input carry. Here also the multiplexer output is B bar. Here A plus B bar plus 1. This is the actual subtraction. And again I am going to be consider 1 0 and input carry equal to 0. 1 0 means actually the second input of the multiplexer, right? This is turned as the output, that equal to 0. So all the zeros are transferred and A is transferred. So ఇక్కడ all zeros are transferred. Simply A, that means simply transfer. That means what happened here means A plus 0, that equal to A. Suppose again I am going to be write like that. I am going to write 1 0, and there is an input carry. The all zeros are transferred, but A plus 1, because this operation is D equal to, you write A plus Y plus C in, right? A plus 1. This is known as the increment operation. And we are 1 1 and 0. 1 1 means the final input of the multiplexer is turned as the output. That means the final input is actually all ones. We know that all ones means this is minus 1 actually. Hence we are going to write it as a minus 1. This is the decrement. Again 1 1 and 1, here also all ones transfer to the input to the multiplexer. This value is minus 1. Now a minus 1 plus 1, that is again transfer is happen. Friends, here you can understand due to the space problem, I am going to be represent only one stage of the arithmetic circuit, but we are going to be write it as a draw actually in four stages consisting of four boxes like that, because in the description I am going to be say that we are going to be construct the 4-bit arithmetic circuit. So it actually has the four boxes, but space problem I'm going to design only one stage of the arithmetic circuit. I hope you can understand this one. Thank you.